When we started this lecture series, there were three things that we had in mind regarding projectile motion. Number one, the time of flight. Number two, the range of the projectile. And number three, the maximum height to which the projectile rises. Now we have covered the first two in the earlier lessons. In this lesson, let's find the height of the projectile. Turns out that as long as the projectile lands on the same horizontal plane, the maximum height of the trajectory occurs at the midpoint of its flight. This is because the path is symmetric around the midpoint. A different launch angle would lead to a different maximum height. In fact, the greater the launch angle, the greater would be the maximum height. But what we want to do is to fix the angle of the launch and to fix also the initial speed of the projectile. And having fixed both these, we want to find the maximum displacement from the ground. Again, we make use of the concept that we have been making repeated use of in this lesson, and that is, we work with the motion's equation independently along each axis. And since we want to measure the height along the y-axis, we will set up the motion equation along the y-axis. Let's use the third equation of motion along the y-axis. So we have Vy squared equals V0y squared plus 2ay minus y0. And we make use of another concept along the y-axis. At the topmost point in its flight, the component of velocity along the y-axis is 0. So now we consider the motion of the projectile from the launch point to the topmost point. So in this case, the final velocity Vy would be 0. Also, along the y-axis, the acceleration would be pointing downwards, so it would be minus g. So here a would be minus g. The final displacement y would be the maximum height, because we are considering the motion from this point to this point. So the final displacement y would be the maximum height h, and the initial displacement here would be 0. Also, as always, the initial velocity v0y would be v0 sine theta. Making the substitutions, we obtain the maximum height given the initial speed v0 and the launch angle theta as v0 squared times sine squared theta over 2g. You can see that this derivation is quite simple since we limit the equations of motion to just the y-axis. From this formula, it is quite clear that the maximum height will increase as we increase theta, or as we increase the initial launch speed v0. Also, if we launch the projectile vertically upwards with the same initial speed v0, this would give us the greatest height that it can attain. With this, we now know the time of flight, the range, and the maximum height attained by the projectile. We've dealt with the same problem in the earlier lesson, but there we computed the time of flight and the range, and now we compute the maximum height attained by the projectile. So we have a projectile that is launched at 70 meters per second with a launch angle of 45. So substituting this into the height equation, we get the maximum height attained as 122.5 meters. The maximum height attained by a projectile which lands on the same horizontal plane is measured at the midpoint. The maximum height depends on the speed with which the projectile is launched. The greater the speed, the greater is the maximum height attained by the projectile. The launch angle also determines the maximum height attained by the projectile. The greater the launch angle, the greater the height attained by the projectile.